y'all. Get keen, get freaking keen, y'all. I hope I'm live. Give me 2 seconds. Is it live? It looks pretty live. All right, guys, she's alive. Welcome to the UNSW MathSoc 2018-2019 revision session. It's gonna be pretty freaking hectic. We're gonna go through some mathematics. It's gonna be crazy. Um, I hope you've all been having a wonderful StuVac so far, and are ready and prepared for the absolute hellstorm that is going to be your exam. Get freaking keen. Just to quickly introduce myself, I'm Tim. I'm one of the academics directors at MathSoc. I study maths and electrical engineering. And I'm going to be taking you for the first hour, hour and 15 minutes, depending on how fast I speak, which is a very variable thing. Depends how long we're going to be together. The plan for today is I'm going to be taking you through functions of several variables, extreme values, vector calculus, which who knows how long that's going to take. And then you're going to have the absolute pleasure of Mr. Riz God himself, William Wu, is going to be taking you through matrices. That's today. That's the plan for today. But of course, that's not the entire course. So stick around. Don't stick literally around here. But on Thursday, I think it's Thursday. Don't quote me on if it's Thursday. It's another day. You're gonna have the absolute behemoth of a massive brain, Ann Chen. She's gonna be taking you through ordinary differential equations and stuff like that. And then the goat, the king, God himself, Gerald Huang, is going to be taking you through the rest of the course. So get keen for that. But for today, we're going to be going through some of the spicy multivariable calculus that everybody knows and loves. Now there is a chat. I guess I can check the chat. My voice is echoing. That's really annoying. Thank you to whoever chucked that through. Let's see if I can fix that. So give me 2 seconds. Let's go to let's switch off this. Okay. Look, if it hasn't fixed itself, chuck a message in the chat. And I will figure out how to fix itself. I will figure out how to fix it, which should be fun. That's also very annoying. But oh well. In the meantime, let's jump into my favorite. I'm kidding. One of my favorite topics, functions of several variables. I'll check back in a minute because there's like a little bit of a delay with the stream. Okay, so functions of several variables. Wowzers. You have a function that's made up of multiple variables. So hopefully by this point, most of you have seen these before. You saw them back in like Math 1B. Is my voice fixed? Dunno. You saw them back in Math 1B. They're very useful, all right? Most things in real life don't just depend on one variable. They depend on multiple variables. So it's very useful to have multiple variable functions, which is cool and stuff. Now, one of the things that we immediately want to do when we get a multivariable function, in fact, when we get to most things in maths, is the first thing we want to do is we want to define calculus on it. And that's what multivariable calculus is. Now, the most fundamental idea in multivariable calculus is the idea of a partial derivative, which is essentially if you have a normal function, you've got your beautiful like f of x equals whatever the hell it's equal to, you can differentiate it by doing your like derivative rules on functions. And in the same way, you can have a partial function. The only difference is instead of using d, we write this like Montarac looking thing that's like a backwards 6. That allows us to take a derivative in whichever direction we like, which essentially means instead of analyzing how like a 3 or 4 or 17-dimensional function acts in like all the directions, we can figure out how it's going to act in a particular direction. My mic's not working? Guys, I'm sorry. Okay. Time for some technical difficulties. Let's say thanks, guys. I really appreciate it. Let's see. Okay. Fix it. Guys, this is some MathSoc behind the scenes. All right, y'all. Let's take a cheeky look. I'm gonna wait and see. In the meantime, did you hear any of that? Because that would be very exciting if none of you heard any of that. Let me get the stream up on my phone to check that out behind. But anyway, thank you all to everyone who rocked up. I didn't actually like expect that many people to come live. Like usually what happens is a lot of people watch the lecture like later on. So thank you all for coming. I'm going to Okay, it seems to be working out. I'm actually going to have the chat up now on my phone. So I'll be able to see you. Anyway, I'm going to just really quickly run through everything that I said beforehand. So TLDR, I'm going through the first three topics: functions of several variables, extreme values, and vector calculus. Then Bestie Rizla William Wu is taking you for matrices and stuff like that. And then on Thursday or whenever, Anne and Gerald, absolute king and goats, will be taking you through the second half: ordinary differential equations, Laplace, Fourier, and partial differential equations, which is very fun. Because you're here, chuck some chat, chuck some things in the chat whenever, if you have any questions, because I now can see the chat. Look at this. This is stuff that I probably should have prepared before the stream, but I was focused on getting you hot, sexy slides, which, by the way, all of these slides, you'll get access to once we're finished on like Thursday or whenever the second session is, because we'll upload them to like the MathSoc page and stuff. Anyway, back to partial derivatives. I'm sure most of you are fairly comfortable with partial derivatives, so I won't spend that much time on them. But the TLDR is you just, whenever you're taking the partial derivative of a particular variable, you just treat all of the other variables like constants. So for example, here we've got consider the function z equals f of x of some gross ass looking thing. And we're asking, is f an increasing or decreasing function in the x direction at the point 0 pi on 2? Okay, so because we're interested in the x direction, that's a cheeky hint that what we're going to be doing is taking the partial derivative in the x direction. Very cool. So to take the derivative in the partial derivative in the x direction, we're going to treat all of the other variables as constants, i.e. we're going to treat y as a constant, and then differentiate with respect to x, right? So df or dz, or del, sorry, I think is what we call it. Del f del x is equal to the partial derivative of x squared, which is going to be 2x times, then we just treat y like a constant, so y cubed, plus then our partial derivative of e to the 4x sine y, which is going to be 4e to the 4x sine y. So basically, anything that has y, i.e. like our y cubed, our sine y, we just treat them like constants. Imagine that they don't exist, they don't even affect our function. Then we differentiate with respect to x. Now that we've got our derivative, hopefully that makes sense to everyone. Chuck any questions in the chat if I can scroll up a little bit more. Sorry, Julian. Love you, Julian. Hugs and kisses. Okay, so we now have our. Okay, hopefully you can see the. Oh, my face is in the way, guys. I'm going to move my face. My face is now up there. That's a good point. Okay, hopefully you should be able to see the rest of the question now. Okay, now we have that point. We're going to now we've got our partial derivative. We're going to sub in the point 0 pi on 2 to figure out, is that actually increasing or is it decreasing? Now to fix that, what we're going to do, we're just literally going to plug it in, and then depending on whether it's positive or negative or 0, that tells us whether or not it's increasing or decreasing. So at that particular point, del f del x at 0 pi on 2 is equal to 2 times 0 times pi on 2 cubed. Now, of course, because we're multiplying by 0, all of that is just going to disappear, which is lovely, big slay. And then we've got 4e to the 4 times 0 times sine of pi on 2. Now, sine of pi on 2 is 1, so I guess we can just make that disappear. And e to the 4 times 0 is also 1, which is very convenient. Thank you, whoever wrote this question. And then that then means we can sub in, it's just going to be equal to 4. Now, 4 is positive, 4 is greater than 0, therefore we know that it is increasing here. Hopefully that makes sense to everyone. If through any of these questions, also if I don't get through all of the questions that I've got here, I have written up very hot, sexy solutions on my slides. So of course, when you get your slides after, you will be able to go back through and look at all of those worked out, hot, worked out LaTeX solutions, which is very, very cool. If anyone has any questions on that, chuck them in the chat. Otherwise, we will move on to the multivariable chain rule. So you've got your normal chain rule, which like in normal variable calculus is sort of like, let's say we've got f of x is equal to like x plus 1 to the power of 30. And the way we differentiate this, rather than literally multiplying 30 different things out, is we sort of take the derivative of the outside function, in this case to the power of 30, and then we multiply it by the derivative of the inside function. And in the same way, if we take the partial derivative of some function like this, we use a multivariable chain rule. Now, in this question, we have some function u equals x squared plus 4y, where x equals 3s times t and y equals 4s times ln t, and we need to find the partial derivative of u with respect to t and the partial respect of u with respect to s. Now the way we're going to do this is using this multivariable chain rule. Now I have written out the multivariable chain rule down for you here, but of course it looks pretty like gross and disgusting. So essentially the way that I like to think about it is it's very similar to how if you did like extension 1 maths, for example, in high school, it's very similar to how you might have used rate of change questions, where like say you know what like dH dr is equal to, you know what like dr dt is equal to, and you want to find out what like dH dt is equal to, you would multiply these two fractions together. So you would do like let me clear up some space. You would do like dH on dr times dr on dt, cancel out those drs, because fractions do fractiony things, and that would leave you with dH dt. In the same way here, we're basically just taking the derivative of z with respect to each of our like internal variables, and hopefully crossing our fingers, if we do it all correctly, all of the things that we don't like will cancel away, and all the things that we do like will like stay there. Now, for the sake of time, because we've had a couple of technical difficulties, I will just work through our del u del t, but it's essentially going to be the exact same process for dl ds. So if we want to find del u del t, what we're going to do, and I might actually zoom out a little bit, just so I've given myself a little bit more space. Okay, so del u del t is going to be equal to del u, and because our u isn't actually directly made up of t, what we're going to do instead is we're going to split it up into the two things that it is made up of, right? It's made up of x, so we'll do del u del x plus del u del y. Del is at least what I'm calling our like backwards 6. Honestly, now that I think about it, I'm suddenly having a slight existential crisis about what our partial derivative sign is called, because it like in LaTeX, which I feel like is the only main source of me actually having to verbalize maths things, you call it partial, and so I guess I could just say partial u partial x, like that might make sense. Where did del come from? Oh well. Anyway, so we've got our two del, like our partial u partial x, partial u partial y. But of course, that's not in terms of like t, right? We want to figure out what our partial derivative is with respect to t. So in order to figure out, we multiply both of these partial fractions, partial derivatives, by their respective like partial derivatives of the things that we're finding, of the things that we're like differentiating with respect to u in terms of their things inside. So we'll multiply this by del x on del t, and we'll multiply this bad boy by del y on del t. So now you can see that like our x's will cancel out, our y's will cancel out, which will just leave us with a beautiful expression for del u del t. Now, of course, if you want to, you can literally just substitute your expressions in. And for a question like this, that's actually a viable like strategy. I don't think that there's anything particularly wrong with doing that. It's just that as your question becomes more and more complicated, it's going to become grosser and grosser and grosser to actually do that. So I'd recommend being on top of the chain rule is pretty nice. Anyway, now we've gotten that out of the way, we just essentially have to go through and take a whole bunch of partial derivatives. So looking at our expression for u del x is going to be equal to 2x. And then del x del t is going to be equal to, well, differentiating this with respect to t is just going to be equal to 3 times s. Plus then our del u del y is going to be 4, because like the derivative of 4y is just 4, and then del y del t is going to be the derivative of this, which is going to be like 4s divided by t, so that gives us 4s on t. Now we're almost done. We've almost got our final solution. So for 2x plus 2x times 3s plus 4s on t. But there's still one more problem, which is just we want to find the function in terms of s and t. And so now we come back and we substitute in for our expression of x, we substitute in 4s ln t. So that ends up giving us 2 times 4s ln t times 3s plus 4s on t. Combining all of that hot stuff together, you can do like the mental maths in your head, because I think you're going to end up with 24 s squared ln t plus 4s on t, I think is our go. Don't quote me on that. I did do that in my head. We'll see. But that's how we use the multivariable chain rule. If you've got any questions on that, chuck them in the chat and I will see them. Okay, next thing that we're going to take a look at is our Taylor series. Now, Taylor series is basically, in first year maths, we learned you can express any kind of function as a power series of a whole bunch of like expressions of our like function around a particular point. Now, if you have multivariable functions, there is a very easily generalizable formula, but even though the formula is very easily generalizable, the actual computation of our Taylor series becomes like really, really munted really, really quickly. So because of that, so this is what our multivariable Taylor function looks like. So it's sort of like, instead of taking the first derivatives, we take the partial derivatives of every single point, and then for the second like order terms, instead of taking we like basically take every single possible combination of second order terms. So like we have the second order partial derivative with respect to x, we've got the second order partial derivative with respect to y, and then we've got the second order partial derivative with respect to both x and y. Now, theoretically, you could continue with that, right? You could go on to third order terms where you've got like the third order partial derivative with respect to x, the third order partial derivative with respect to y, the second order partial derivative, which has like 2 with respect to x, 1 with respect to y, and then the one with 2 with respect to y, 1 with respect to x, and so on and so forth. However, for the purposes of this course, like basically we will never really go beyond second order terms, and we will also never really go beyond like 2-dimensional Taylor series. Like you can technically express it onto infinite dimensions, but we don't, because it's hard and we're lazy. And if we needed to, we would just get like MATLAB or Wolfram or Maple to do it, because they're computers who can do it pretty quickly for us, which is very lovely. Hugs and kisses. Okay, so let's have a go at this Taylor series here. So consider the scalar field f of x equals sine x plus y squared. And we want to calculate the Taylor series expansion of the function around the point 4, 4 up to and including the quadratic terms, which is very, very cool. Now, the way we're going to do this is we're basically just going to be plugging everything into this formula. So the the gross thing about Taylor series is, yes, it is disgusting formula. That formula is gross and yuck, and I don't like it. However, the fun thing about Taylor series is it's really freaking formulaic, all right? You just have to plug and chug, all right? You take your derivatives, you plug them into the formula, wowzers, full marks, 100 wham, okay? That's how it works. Okay, let's calculate the Taylor series expansion around the point 4, 4 up to and including the quadratic terms. When it says quadratic terms, we just mean the second order degree terms, because each of these terms has a quadratic in it rather than like a normal thing. Okay, so the first thing we're going to do is substitute our point 4, 4 into the function. So what is, like, this is finding our, I guess, 0th order term. So the function at 4, 4 is equal to sine 4 plus 4 squared, so 4 plus 4 squared, which is equal to sine of 20, which is equal to a number. Who knows exactly what it's equal to, but you know what? We can probably assume that we're talking in radians. Let's plug that into our formula, and it's equal to like 0.9. Coolio's, it's equal to 0.9. Let's maybe chuck that in, because, you know, we're engineers. We like approximating things. Exact value, who is she? Don't know her. Okay, so that's our first order term. Coolio's, let's do some second order terms. And let's spice it up. Let's pick a different color for second order terms. They have second order terms as red. Let's do second order terms as red. So in order to do our second order terms, we need to take our in order to do our first order terms, we need to take our first derivatives. So taking del f del x, calculating the derivative at the point x, we're just differentiating this thing at x. And of course, if we differentiate like sine of x plus y squared. Well, the derivative of x is just 1. So we end up with cos of x plus y squared. And del f del y is just going to be equal to 2y cos of x plus y squared, right? We're just differentiating y squared and slapping it out the front. Now that we've got that, what you can see is that we're actually evaluating our first derivatives at that particular point. So we can find what is our function equal to at the point 4, 4. Well, that's going to be equal to, for the derivative of x, we're going to end up with cos of 4 plus 4 squared, which, because we calculated it before, is equal to cos of 20. I was talking about we've calculated the 4 plus 4 squared, not the cos of 20. What is cos of 20 going to be? Is it just going to be 0. Never mind. Cos of 20 is something completely different. That's fun. It's like 0.4. Let's check that in. 0.41. And then the derivative of f with respect to y at the point 4, 4 is going to be equal to 2 times 4, which is 8 times cos of 20 as well. So it's going to be what we just calculated, multiply that by 8, which gives us like 3.26. Which is very coolios. So that's our second order, that's our first order terms. Then all we have to do is, let's go even further and calculate out all of our quadratic terms, which is really exciting. Okay, so first of all, and because they did these ones in blue, let's make our hot partial derivatives blue as well. So taking the second order partial derivative of f with respect to x, we end up with minus sine x plus y squared. And taking the second order partial derivative with respect to y, we end up with, oh, that's going to be gross. We're going to have to use chain rule. Disgusting. Okay, doing that quickly, we should end up with 2 cos x plus y squared minus 4y squared sine x plus y squared. There. And then we just want to take the partial derivative of x with respect to y. Now, for this second one, essentially what we're looking for is we're trying to figure out this partial derivative here. Now, just quickly note, because of one of our hot theorems, it doesn't actually matter which order we take our partial derivatives in, i.e. we get the choice. We could either differentiate this one with respect to x or this one with respect to y. Now, in this case, I don't actually think that there's an easier one to go with. I think that they're pretty much both identical in that neither of them is especially hard. I reckon this one's probably decently nice to go with, because remember, if we're taking the partial derivative with respect to x, we just treat y like a constant. So it means when we take that second derivative, f of del x del y, that ends up being equal to minus 2y sine of x plus y squared. Then we have to go through and we have to sub in all of our points. So when we sub in 4, 4 here, we're going to get minus sine of 20. When we sub in our points here, we're going to get 2 cos 20 minus something, minus 4 cubed, minus 64. So minus 2 cos 20 minus 64 sine of 20, and when we sub in our points here, we're going to end up with minus 8 sine 20. So very hot, cool. You can evaluate all of those, and then you just construct the full equation. So now we have all of our points. You know, we may as well just go through and quickly evaluate those. That's minus 0.913. That's going to be 2 cos 20 minus 64 sine 20. Also, if I made like a calculation mistake, please call me out on it, because, you know, I'm a math student. That doesn't mean I'm actually good at plugging numbers into a calculator, which is unfortunate. Okay, so that gives us all of our numbers that we love and we cherish. So now that we have all of our values, we can essentially go back through and use them all to construct our Taylor series. So we can say f of x is going to be equal to 0.913 plus our first partial derivative, which was 0.41 times x minus 4 plus 3.26 times y minus 4 plus, or minus 0.913 x minus 4 squared minus 57.61, x minus 4, y minus 4, and then our final term, minus 7.3, y minus 4 squared. And that is our very, very hot Taylor series. Now, as you can see, quite a bit of working out, all right? Quite a bit of effort to get that final Taylor series. But on the flip side, it was really like there was nothing especially complex. I did actually make a mistake, I just realized. So we want to make sure that our second order terms, we divide them by the power of 1 on 2, right? That's just a direct extension from our first order Taylor series. So sorry, every single term after here should be divided by 1 on 2. Sorry that I didn't do that. But yeah, coolios, that is our Taylor series, which is very cool. If you have any questions about that, chuck them in the chat. But otherwise, we are going to take a look at our applications of error approximations, because sometimes, disappointingly, we have to take care of like what our error is in a particular estimation. We can't just say like, oh, error has gone poof, because that's what I do a lot of the time. Cheeky story, one of my favorite things that I have ever seen in an engineering lecture was the approximation 10 plus 7 is approximately 10, which like, pop off king, but also I don't know if that's a valid approximation. Okay, let's get a move on. So when we're making applications to error approximations, this is essentially just an immediate extension of our first order Taylor series. So you can see here, if we sort of move this term to the other side, wowzers, we've got our Taylor series with one-dimensional things. And it's basically a way of putting a hard upper bound on how much error there might be in a particular measurement. So once again, these kinds of questions are fairly formulaic. Where essentially you want to take partial derivatives and multiply them, each of them, by their respective uncertainties. One quick point that I don't think I included in this formula is that these partial derivatives should be evaluated at the particular values that you have, at the particular points that you have. But otherwise, like, it's essentially another example of good old chug and plug, which we love. Okay, so speaking of chug and plug, let's get chugging and plugging. So the first thing we have to do is in this question, we are given the volume of a cone with radius r and perpendicular height given by that. We want to calculate the maximum absolute error and the maximum percentage error in calculating v, given that r equals 5 centimeters and h equals 3 centimeters to the nearest millimeter. Okay, coolios. So the first thing we have to do, of course, is we have to take all of our partial derivatives. So del f, del x, which in this case, we can sort of write the equation is in terms of r and h. So I guess let's find the partial derivative of f with respect to r. So that's going to be 2 on 3 pi r times h. Then we want to find the partial derivative of del f with respect to h. So in this case, this is going to be 1 on 3 pi r squared. And now that we've evaluated all of our partial derivatives, we actually want to sub in the particular values we've got. So, right, we've got r equals 5 centimeters and we've got h equals 3 centimeters. So let's sub them in to actually figure out, like, what are the magnitudes of our partial derivatives at these particular points. In this case, it's 2 on 3 times pi times 5 times 3, which I think is going to end up being 10 pi. And then we've got 1 on 3 times pi times 5 squared, which is going to be 25 on 3 pi. All of a sudden, I'm very much doubting myself, but hey, if I have made a mistake, chuck it in the chat, call me out on it. I'll give you my eternal love and affection. All right, that's what's up for grabs today. Now, the next thing you would do is that if one of these were negative, you would take the absolute value of that. The reason for that is we're looking for absolute magnitude of error. Both of these are already positive, so we don't have to do that here, which is lovely. The last thing we then need to figure out is our uncertainty in delta x and delta y. Now, this is the only point where you sort of have to do a bit of cheeky abstract outside the box thinking, where physically what you would do if you were doing this in an experiment is you would look at the lowest like resolution on your measuring equipment and then take half of one of those increments, right? So let's say you're using like a scale and it measures to the nearest gram, then your uncertainty would be half a gram. Let's say you're using like a Smith chart and it measures to like the nearest half degree, then your uncertainty would be 0.5 times of a degree. It's just half of whatever your nearest unit is. Now, here, we obviously can't look at the ruler that was used to measure r and h, so I'm just going to make some numbers up. So I'm going to say, also, I'm very sorry.
I seem to have just suddenly gotten a blocked throat. So I'm sorry if my voice sounds really weird all of a sudden. We'll sort that out. Look, today has been a day of fun overcoming things. Alrighty, so we have r equals 5 centimeters and h equals 3 centimeters. Because both of these measurements are in like exact precise centimeters, we're gonna make the assumption that our like maximum precision is probably around about 1 centimeter. So therefore, our maximum uncertainty would be half a centimeter. So we could say that like our change in r is equal to our change in h is equal to 0.5 centimeters. Now, usually you should be given some sort of like reference point for this, whether it be like an actual diagram of what like the ruler is that's used. In this case, I think it's a fair assumption to say, wow, it's like around about that much. Now, once we've got all that, we can actually chuck this into our formula and we can say, wow, our change in our formula, our absolute error, has to be less than or equal to our partial derivative with respect to r, which is 10 pi, times our uncertainty in r, which is 0.5, plus our absolute uncertainty in our absolute uncertainty in h, so times 0.5, which if we chuck all of that into your calculator, you end up with 5 pi, 5 plus 25 on 3 times 0.5, which ends up with a value of like, you end up with a value of like 9.167 pi. Honestly, at this point, I may as well just evaluate it, hey, because like pi times our 5 times plus 25 on 3 times 0.5, which gives us like 28.79. Now, this is currently a measurement in centimeters cubed, which is unfortunate because we want the measurement in millimeters cubed, which is not great. So when we want to do that conversion, each centimeter has 10 millimeters. So if we've got this many centimeters cubed to convert it to meters cubed, I think we're going to have to multiply it by 1,000, which gives us a pretty large error in millimeters, which is not very cool. But that's how we would do it. That's essentially the main strategy. I realized that I have spent, what's the nearest millimeter for? Sorry, I think I probably meant to say millimeters cubed when I wrote the question. The nearest millimeter, oh, I see what you mean. Sorry, I think I may have misinterpreted the question when I looked at it the first time. So I interpreted it as we want to calculate the nearest error to the nearest millimeter, but I think what Ezra may have pointed out is that the R values are actually saying that we have measured these values to the nearest millimeter. See, that actually checks out a lot more because I was looking at this number and I was thinking, God damn, that's some like pretty massive error like issues things, right? Because like that shows us that we obviously have some really horrific looking measurement instruments, which is not very fun. So let's actually go back and let's say that our uncertainty for both of these is 0.5 millimeters, right? So that's in centimeters. That's going to be 0.05, right? So plug both of those in instead. So 10 pi times 0.05. So the reason we're doing that is because assuming that we have precision up to the nearest millimeter, that then means that our biggest uncertainty is going to be half a millimeter, which is 0.05 centimeters. The reason I'm using centimeters is just because these measurements are in centimeters. So long as you convert them as 1 point, actually, now that I think about it, let's continue with the train. We'll convert back into millimeters at the end. So 10 pi times 0.05 plus 25 pi on 3 times 0.05 down there gives us a much nicer, much more reasonable value of 2.87 centimeters cubed. 2.8797, which is around about 2.9 centimeters cubed, which we can convert into millimeters. Or honestly, considering the reason I was thinking of converting it into millimeters beforehand was because I had thought that this was referring to the nearest millimeter. I think that then means we don't need to convert it into millimeters and we can just leave it in centimeters, which is very cool. Hopefully that makes sense. I'm very sorry for that mistake, and also big shout out, hugs and kisses to Ezra for pointing that out because I completely misinterpreted it. But lovely. Hopefully that makes a bit of sense to you guys. If you have any questions, chuck them in the chat. let's move on. That's what I was meaning about you would look at the thing. And yes, Ezra, you were right. It is 0.05 centimeters. Let's move on to our next fun thing, because I've realized I'm going quite slowly, which is Leibniz's rule of however you pronounce his name. Now, this rule is essentially a cheeky trick that we can use to evaluate either. Sometimes you happen to have the situation where you're trying to evaluate the derivative of a particular function that you're integrating. But in other cases, you can also use this rule to just evaluate really hard integrals in the first place. Now, the basic idea is if you're differentiating some function that integrates from over two rules, you use this gross looking formula to evaluate it. Just breaking this down, it's essentially now you're integrating under the partial derivative of whatever your original function was in terms of. Then you add sort of the upper bound on, and then you subtract the lower bound on. Intuitively, the idea for this formula basically comes because it is quite gross and quite big. I have a couple of strategies that I like to use to understand where the different pieces of this formula comes from, right? So intuitively, the value of this derivative should increase if the function of itself increases as well, right? And that's essentially what we have here. That's what we have. This integral stays there. If f of t gets bigger, then our function, the integral, should also increase as well. If this function here increases as well, because essentially that we can interpret as we're integrating under our curve further and further ahead, that means that our integral is going to increase as well, and that's why we add this next term on. That's why the next term is a positive, versus if our lower bound increases, i.e. if we're shifting our lower bound up even further, we're bringing our lower bound closer and closer and closer, that means that the area under the curve, our integral, is going to decrease instead. So that's kind of the full formula. I feel like with this kind of case, it will make a lot more sense once you've started to do some questions. So don't just look at the formula, actually jump into some questions. Now, I wanted to quickly point out, if you have a function that has constant bounds, i.e. rather than functions, because your derivatives of those functions are constant, all of your other terms pops out, and you actually get quite a nice looking formula. Now, just as a general rule, I don't want to say that this is for everything, but in terms of exam questions, it tends to be if you're literally taking the derivative of an integral, i.e. you've got some integral, we don't care about actually evaluating the integral so much as we do about taking the derivative. In that case, you will have functions as your bounds. Essentially you have some function at the top, some non-function down the bottom. Whereas if what we care about is having some gross looking integral and we want to just find a way to integrate it in the first place, in those situations, that's where we're much more likely to be using this rule instead, where essentially our bounds do have some kind of our other terms disappear, and we're just rearranging the equation to express it as another derivative. That all being out of the way, let's actually go ahead and let's try and use Leibniz's rule to evaluate some integrals, which should be very, very fun. So in this first case, we want to find the derivative of the integral of 1 on y sine of xy times dy from minus x squared all the way up to x. Now looking at that, she's a bit gross, all right? That's not a very fun integral to have to evaluate. So instead, what we're going to try and do is we're going to use Leibniz's rule. I've realized now I've changed pronunciation of how I've said it 3 times. So please, if there's one thing you've taken away from this revision seminar, it's that I can't pronounce or speak maths things, all right? Some of my pronunciation is not the official mathematics way, it's the Tim way of explaining stuff. So good thing that maths exams are written and not oral, because otherwise I would lose a lot of marks. Okay, so in order to do this, we're going to use the first Leibniz's rule. So we want to find the derivative of from minus x squared up to 2x of 1 on y sine of x times y dy. Now to do that, we're going to use our big Leibniz formula. So I'm going to scroll back up so that we can kind of see it up here in the corner. So the first thing we have to do is we have to now evaluate the integral after taking the first partial derivative with respect to x. And the reason that that's so powerful here, I might just quickly rewrite the question up here instead. So we want to take d on dx, integral from minus x squared to 2x, 1 on y, sine of xy dy. I encourage you, by the way, if you want to have a go at this question by yourself, just because I feel like with this rule, it is really pedagogically valuable to just have a go at doing it yourself. But otherwise, what you can do is you take the derivative of your internal function with respect to x. And the reason that that's so nice is what you might see is when you differentiate this internal thing with respect to x, your y comes out the front, and suddenly that gross 1 on y, which was probably most of the reason why we didn't like the idea of integrating this thing in the first place, suddenly that disappears, and we're just having a great time instead. So if we put that in the middle, we now have the integral from minus x squared to 2x times the partial derivative of sine 1 on y sine xy, which is going to be cos of xy times dy. Then we add in our function evaluated where we sub in the upper bound. So in this case, it's going to be 1 on our upper bound, which is 2x times sine of, this is where it just becomes grindy, right? It's going to be x times 2x, so 2x squared, times the derivative of that top function, so times just 2, and then minus our next term, which is going to be f of, 1 on minus x squared, so that ends up being 1 on plus 1 on x squared times sine of x times minus x squared, so minus x cubed times the derivative of minus x cubed, which is going to be minus 2x. So all in all, that ends up becoming minus 2 on x sine of minus 3x. So minus 2 on x sine of minus 3x, which was a little bit grindy, but essentially was just, we're going to plug numbers in and they were going to pop out nice. We still have this integral that we have to evaluate, but now because we're taking the integral with respect to y, we can just treat x like a constant, right? So we can just treat this like we would integrate any kind of like integral of cos of like ax, that's going to be equal to sine of 1 on a times x. So we can plug that in. We're evaluating 1 on x sine of x times y, where our bounds y are 2x and minus x cubed, which is equal to 1 on x sine of 2x squared minus 1 on x sine of minus x cubed. And what you might notice is that we now have these like common sine 2x sine minus 2x. So if we sub this expression, and I'm sorry, my working out's a bit all over the place here, but if we sub this expression back into our integral, that then will give us, I believe it should be 2 on x sine of 2x squared minus 3 on x sine of minus x cubed. Once again, don't quote me on that because that was very much like a rapid in my head kind of evaluation. So yeah, don't trust that 100%. But that is what our integral could look like. Okay, it looks like I got the first term right, but something went funky with the second term. Oh well, everything else looks pretty good. Now, another way you can use Leibniz's rule is to evaluate these kinds of integrals, where essentially you have some kind of integral and you want to, like, you're given some kind of integral and you want to use Leibniz's rule to solve it. The TLDR here, right, is what we can do is we can see that this internal thing is the derivative of that thing there. So therefore, we can write this integral here, which is the integral of the derivative of this thing, must then be equal to the derivative of this thing. And just for the sake of time, because I've realized I've spent a lot longer than I had expected, if you want to look at this question, I have written out the answer here. So you'll see that because we're differentiating a constant, we get 0, which is very fun. And you can work through that there. So that's all of our functions of multiple variables. Let's move on to extreme values, which is essentially our multivariable form of optimization. So when we're dealing with this kind of situation, what we're looking at is we're trying to figure out where does our function reach its maximum point, where does it reach its minimum point, and sort of like how in one-dimensional functions you have those points called inflection points. Instead of having inflection points in multivariable functions, we have what are called saddle points, right? You can see here in this little diagram, they're called saddle points because they look vaguely like a saddle. Now, hydrate, dihydrate. like how for univariate functions, we find the critical points of a function by figuring out where the derivative is equal to 0, whenever we're dealing with a multivariable function, we try and figure out the points where all of our partial derivatives are equal to 0. Basically, we figure out our max and min in the one-dimensional case by figuring out, oh, here's the point where we're not moving anymore. And in the same way, in multivariable functions, we just figure out where all of our partial derivatives are equal to 0. Essentially, we figure out where all of them have stopped moving, which is very, very cool. Now, so yeah, essentially, whenever you want to find critical points, you just figure out the points where all of your partial derivatives are 0. We're going to do a practice of that in just a second, but that's sort of like how you find your critical points for the one-dimensional case. You just do the same procedure for your multivariable case, which is very fun. Now, just like in the single variable case, what we want to do once we've figured out what we want to do immediately after we have figured out what our critical points actually are, is we want to figure out, okay, what kind of critical points are they actually going to be? Basically, are they going to be a maximum, are they going to be a minimum, or are they going to be a saddle point? Now, through the power of magical mathematics, we define this expression here. D equals the second order partial derivative of f of x times the second order partial derivative of y minus the second order derivative of both x and y squared. Now, this is just a really good indicator function that helps us to figure out what our classification is necessarily going to be. If you're interested in it, it comes from the way that we classify critical points in complete generality from what are called, I'm mental blanking on the name, I think the Hessian matrices, which is basically we see, are they upper triangular, are they lower triangular, stuff like that. But for the purposes of this course, right, we're engineers, we don't care about the deep mathematics, so instead we just care about this expression here. And the way we use it is using these different rules. So basically, if d is greater than 0 and our partial derivative is less than 0 at the critical point, then we've got a local maximum. The idea there is essentially because x, we have at least one of our variables decreasing, but our thing is greater than 0, which essentially, if this thing is greater than 0, that tells us we either have a max or a min. But then we actually look and we dig into one of the functions and we see, okay, what are they actually equal to? And that tells us whether it's a local maximum or a local minimum. The reason for that is because essentially here, both your x and your y will probably be decreasing at this point. So both of these terms are negative. So when you multiply them together, it ends up with a positive, and that's why your d can still be greater than 0, which is why we have to check both of them, assuming, of course, that we've already made sure that our critical point is essentially all of our first order partial derivatives are equal to 0. Likewise, if d is greater than 0 and our second order partial derivative is positive, that means we have a local minimum. You can think of these if you're comfortable with your first, if you're kind of comfortable with your single variable optimization, you can kind of think of it as wow, your derivative is positive, therefore it's smiley face. Your derivative is negative, therefore it's frowny face. So frowny face means local maximum, happy face means local minimum. And also, just quick side note, the reason we call them local maximum and local minimum is because the function may continue going off to infinity in every direction, so there may not be a global maximum. It also could be a global minimum. And when we look in a second at Lagrange multipliers, we'll see that you actually can find the global maximum and the global minimum. Finally, of course, if d is negative, that then means you found a saddle point. And if d is equal to 0 at that critical point, then lucky you, the test is inconclusive. Generally, that won't happen in an exam if your examiners are nice to you, so you probably don't have to stress about it too much. But generally, my fix for that would just be to plot the function and see oh, okay, what does that actually look like at that point? Because yeah, it could be one or of either of them. It's just sort of a mathematical quirk that ends up happening, which is very fun. So let's practice this. Let's find and classify the critical points of h of x equals 2x cubed plus 3x squared y plus y squared minus y, and we want to find the function values at those critical points. Just side note, one really super easy strategy to figure out if these points are local minimums and maximums is to just find their function value, and wow, if it's the really big one, it's probably a maximum, and wow, if it's the really small one, it's probably a minimum. Just another side note, but let's have a go at finding these critical points. So we have h of x, y. Let's figure out its partial derivatives with both respect to y and x and where they are equal to 0. So the partial derivative of the partial derivative of h with respect to x is going to be equal to 6x squared minus 6xy, and then all of the y's disappear. And then our partial, so, I mean, while we're here, we may as well solve for 0. So we're setting that equal to 0. Let's factorize out that 6x. So we've got 6x minus y equals to 0, which gives us two options. We can either have x equal to 0 and y equal to anything, or we can have x equal to y. Our two possibilities for where our maximum critical points may lie. So let's keep that in the back of our mind now as we look at our second set of partial derivatives, which is our partial derivatives with respect to y. So if we take the derivative of h with respect to y, we end up with 3x squared plus 2y minus 1. And we're solving for this equal to 0. Now, if x is equal to 0 and y equals to anything, so essentially what we're going to do is we're just doing simultaneous equations, right? We're trying to figure out where both of these conditions are satisfied. So starting off with this first condition where x is equal to 0 and y can equal anything, we sub x equal to 0 in, and that gives us 2y minus 1 equals 0, which means one of our maximum points is going to be the point 1 and 1, sorry, 0, 1 on, and 1 on 2. Sorry, I said maximum. One of our critical points is going to be 0, 1, and 2. And then the other thing we're going to do is sub x equals to y in, so that then gives us 3x squared plus x minus 1. And yuck, we're going to have to solve the quadratic equation. So exciting. So we'll do that. So we get x is going to be equal to minus 2 plus or minus the square root of 4 minus 4 times minus 1 times 3. Actually, I think it's going to end up quite nice. This is shocking. First time in my life the quadratic formula has turned out nice in the end. So 4 minus 4 times minus 1 times 3 gives us the square root of 16, so it's minus 1 plus or minus the square root of 16, which is 4 divided by 6, which gives us two potential points, minus 2 plus 4, which is going to be, it could be, I'm mental blanking. This is basic fractions, and your boy's brain has just turned off. I think that's going to be 1 on 3, and then our other one is going to be minus 1. And because we know it has to lie along the line x equals y, that then means our other 2 points are 1 on 3, 1 on 3, and minus 1, minus 1, which is very, very fun. So then you can go through and you can classify all of these and actually evaluate the function at this particular point. Just for the interest of time, I'm not going to do all of them. I'm going to pick one because this one was the first one we found. I feel like I share a bond with it. So let's evaluate it at that particular point. So the first thing we need is we need to figure out, basically we're going to try and evaluate all of our partial derivatives at these particular points. So let's figure out what our partial derivatives are equal to. So the second derivative of the second derivative of h with respect to x, we can go off of this expression here. That's going to be equal to 12x minus 6y. The second derivative of h with respect to y, we can go off of this expression, and that's going to be equal to 2. And then differentiating this, to figure out this one, essentially our second derivative with respect to either x or y, we can just take one of our pre-made partial derivatives and differentiate it with respect to the other one, because why not? I might do, hang on, this is suddenly making me doubt myself because feeling like, did I make a mistake somewhere fundamental back in the process? Guys, this is not looking good. Okay, I did. When I differentiated this, I made it negative for some reason, which is very quirky of me, which means that our line should be y equals a negative x, which is not that big of an issue because it essentially just means coming back over to here, we should make the y negative for each of our x values. So it's 1 on 3, minus 1 on 3, and minus 1 plus 1 instead. I'm hoping that's the only mistake there. The reason I realized that, by the way, is just because we can use that rule that like the second derivative of h with respect to either x or y, it doesn't matter which one you do first, they should be essentially the exact same. And I was like, hang on, if you differentiate this one with respect to x, you get 6x, and then because I had a negative here, you get negative 6x. Your boy done messed up. Anyway, now we've got that out of the way, we can come back to here and we can say, okay, it doesn't matter which one you do, you should end up with 6x as our partial derivative of h with respect once to respect to y, once with respect to x. And because we've done that, like normally you would then go and sub values in, but honestly, because we've managed to get them all generally, it's not that weird of an expression to just sub our partial derivatives in. So if we do that, we end up with, and for some reason I realized my working has like gone upwards rather than downwards. Sorry about that. That's a bit quirky. So let's sub some values in. We end up with 2 times 12x minus 6y. And then minus our 6x all squared. Chuck that in, we end up with 24x minus 12y minus 36x squared, and that is our expression for D. So to test whether or not this, hopefully that makes sense to everyone. If anyone has any questions, chuck it in the chat. Oh, Morgan. Thank you, Morgan, for pointing out that I messed up the partial derivative. I should read the chat more because then I wouldn't have taken so long to realize it myself. Thank you very much. My eternal gratitude. Okay, so coming back to this, let's sub in our points to evaluate the function at the point D. So we get D is equal to 24 times 0, so it's going to be 0, minus 12 times a half, which is going to be minus 6, minus 36 times 0 squared, which is minus 0, which then gives us D is equal to negative 6. So that means D is negative, so it doesn't actually matter what the other partial derivatives are. This has to be a saddle point. And that's essentially how we can go about doing our tests. You can go through, do the other ones. Once again, I have got a hot solution up there for you. And so yeah, you can go and have a crack at that. Now, something that we often are interested in when we're doing these kinds of optimization problems is we're interested in what is our maximum going to be if we have a particular set of restrictions on what we are actually doing. Now, when, for example, here we've got, suppose that the surface area of a cylinder is like 50 centimeters cubed, sorry, 50 centimeters squared, we want to figure out what is its maximum possible volume. Now, these kinds of problems are things that are quite common. We encounter them reasonably frequently when we're dealing with physical things in engineering, because we might be like, oh, okay, we have a box. What's like the largest thing of this shape that we're able to fit in there? And whenever we want to do that using funky, hot maths, we do that using the method of Lagrange multipliers. The technical math speak for this is whenever we're maximizing a quantity subject to a constraint, we use the method of Lagrange multipliers. I essentially think of it as like, okay, we want to figure out what the maximum formula, or like the maximum of a particular formula is. In this case, we're figuring out what the maximum volume is when we have a particular requirement for another formula that involves the same variables, in this case, the surface area. And I feel like it's fairly intuitive when you deal with, like what the problem is fairly intuitive when you're dealing with these kinds of like physical, tangible examples. What's not fairly intuitive is how we actually solve them. So the idea of Lagrange multipliers is if you have some function, in our previous question, this was the volume. So you can imagine you have some function, a volume, we take what's called the gradient of it. Now, the gradient of a particular function is basically where you just have the partial derivatives of all of your different variables expressed as a vector. You would have done this really briefly in 1B. Can't remember necessarily whether you would have gone through this in this term's lectures. But if not, it's essentially just a vector where you take the partial derivatives of all of your different variables and express them in a vector, which is very nice. The reason we call it a gradient is even though it is slightly misleading, it's funny, it doesn't actually point in the direction that the particular function is moving. It points normally to it, so it's always perpendicular to the surface of the function, and that's kind of why we call it the gradient, because like it sticks out from the side of the function rather than like pointing in a particular direction, which is very cool. Now, the way we use this, is we say if we take the partial derivative of some function, then there is some set of lambdas which satisfies this following equation. Basically, if we have our original function and we have our requirement, our constraint that we have, right, where we say in the previous question we were like our f is equal to like our volume function, and then our requirement was our surface area had to equal like whatever it was equal to 50 centimeters squared. So our restraint was our surface area had to equal 50, which you could also write as like surface area minus 50 equals 0. That's what they're sort of saying here about like your function has to equal 0. You can use that to satisfy this particular equation here. Now what that ultimately means, and by the way, this is like just some random variable that ends up, some random constant that ends up being the same for all of them, which is, it's what we call the Lagrange multiplier. It's this lambda thing. Essentially, the way that you solve these questions is you just take a whole bunch of partial derivatives, and then you construct a series of simultaneous equations. So what I might do for this next question, just because once again, I'm conscious of time, I won't go through and solve them all because ultimately what it ends up being is just a really annoying test of your simultaneous equation solving skills, which like you're hopefully at least in second year university, I'm hoping that you can probably, I imagine you can probably solve like 3 simultaneous equation sets. But what I'll do here is I'll just quickly set up what it actually is that we're trying to solve. So let's go back to this example. What is we have the surface area of a cylinder with no base, with a base but no lid, and we want to figure out what its maximum possible volume is, given that the surface area has to equal 16 centimeters squared. So I've got a nice diagram for you here where we've got beautiful cylinder, height, radius, all of that fun stuff. We know that the volume, using like the fact that our volume is going to be the area of our base times the height, is going to be pi r squared, area of the base times the height. And then our surface area is equal to the area of the base, pi r squared, plus the area of the area around it, which is going to be h times 2 pi h, which is the circumference of our circle. Note that because we have a base but no lid, we're only adding this first term on once. And we also know that this is equal to 16 centimeters squared. That's our essentially construction of the equation. You can think of this as being our f, and you can think of this as being our g. Rearranging g, g is just equal to pi r squared plus h times 2 pi r, which I can see I've written down the bottom in a nicer and neater form as being like 2 pi r h. Essentially, all we have to do from here is take the gradient of f and the gradient of g and then set them equal to each other. So if we do that, we should end up, first of all, our gradient of f. You can kind of be arbitrary in like which variable you want to set as variable 1 and which one you want to set as variable 2. Our two variables here are r and h. It doesn't matter so long as you're consistent. I'm going to do r as variable 1, h is variable 2. So partial derivative with respect to r is going to be 2 pi r h. Partial derivative with respect to h is going to be pi r squared. And then similarly for g, we're going to end up with our partial derivative with respect to r is going to be 2 pi r plus 2 pi h. And then differentiating with respect to h, we get 2 pi r. Hopefully that makes sense to most of you. If you don't, chuck some questions in the chat and I can have a cheeky look at them. Nothing else so far. So coming back up here, I'm going to get rid of this stuff. We can then just chuck it into the Lagrange multiplier equation, which says that this gradient is equal to lambda times this gradient. Basically, lambda times f is going to be equal to lambda times nabla of g, which essentially gets us the vector set of equations, 2 pi r h, 2 pi r squared is equal to lambda times 2 pi r plus 2 pi h, 2 pi r, which you can split to get two simultaneous equations. So your two equations are going to be 2 pi r h equals lambda 2 pi r plus 2 pi h, and then our lower one is pi r squared is going to be equal to 2 pi r lambda. Now, one thing that you may have realized is in this equation, we have three variables, right? We've got h, we've got r, and we've got lambda. Which means if we only have two simultaneous equations, but we have 3 variables, we're not going to be able to find an exact solution here, which is annoying because like that was literally the entire point. Like one of the things I promised earlier was that if you use the method of Lagrange multipliers, you have a if you have the method of Lagrange multipliers, you should be able to get some exact maximum and some exact minimum on your function. Which means we need another equation, but luckily the other equation is just our constraint equation, right? Because remember, down the bottom here, I said that pi r squared plus h times 2 pi r is equal to 16. That's going to form our third equation. So we can write pi r squared plus 2 pi r h is going to be equal to 16. And if we include that here, we've suddenly got a system of 3 simultaneous equations where our unknowns are pi, h, and lambda. And essentially, what we want to do is just solve them all. Now, doing that, not gonna lie, bit gross, okay? It's the kind of thing where in real life, you would turn to Wolfram and say, please, please, please and help, please do it for me, do the mathematics. I don't want to do this in my head. However, in reality, in an exam, you can't do that. The side note with that is that Lagrange multipliers don't actually pop up in exams too much because they just take so much goddamn time to solve, which is quite nice. But when they do pop up, it means yuck, good luck. So what I'll do is essentially, because I've already written out all of the working out, if you want to see how you solve all the simultaneous equations, you would do that, which would give you a set of solutions. You would end up with a value for lambda, you would end up with a value for h, you would end up with a value for r. And if you end up with multiple different solutions, essentially what you can do is you can go back to your original function and just figure out the one that has the highest value must be equal to our the one that has the highest value must be our maximum, the one with the lowest value must be our minimum, and all of the other ones are not our global maximum and global minimum. If you don't understand why we would 100% have a global maximum and a global minimum, is essentially just because where usually your constraint is going to be closed. So in this case, the constraint that we have our surface area equal to 16 means that we essentially only have a particular section of our function that we're focusing in on. It's sort of like coming back up here where I have my like little graphs of multivariable functions. It's sort of like we're saying, and oh dear. It's sort of like we're saying back in this function here, imagine that we only zeroed in on like a particular section of this function. Like let's say we only zeroed in on this section of the function. Because it's closed, because it doesn't go off into infinity, that means that 100% we have to have some kind of local maximum or local minimum, sorry, global maximum and global minimum, where our global minimum in this case would be down here, and our global maximum would be up here somewhere. Okay, hopefully that makes sense. Oh, we've got some stuff in the chat. How do you figure out which one would be f, which one would be g? Your function is f, your constraints are g. Absolutely. So in this case, essentially the thing that we're trying to find the maximum or minimum of should be your f, and the thing that like we're told is equal to something is going to be your g. Thank you very much to Yam, and shout out to my homie Yam and Oompa Loompa. Please don't throw me into a chocolate river. That would be unfortunate. Though I do love chocolate. Okay, that's the method of Lagrange multipliers finished. Once again, working's out there if you want to walk through all of it. As you can see, takes a little bit of working out, but you can say that, you know, sometimes doesn't mean necessarily that it's always going to rock up in the exam. Okay, let's move on to my last topic for today because Mr. Rizzler himself is wanting to get on to you guys. Vector calculus, let's take a cheeky look. So, couple of basic ideas that we have to get out of the way before we can actually look at doing stuff with vector calculus. First of all, the idea of a curve. A curve is kind of a fancy formalized word for all of our funky wiggles that probably every maths teacher that you have ever had has been writing. Now, even though there is like a really nice general equation, which is like we can express it as like c of t equals some function, and then we can vary it, like express it out between some start and end point. Just as a personal side note, 99% of curves that you're going to deal with are just going to be straight lines between a start point and an end point. So don't stress about, oh man, how in the hell am I going to parameterize a function that looks like that? Because don't worry, you're not going to have to. Because I look at that and I'm like, I don't know how the hell I'm supposed to parameterize that. Most of the time, it's just going to be You have some start point, let's call it A, you have some end point, let's call it B, and you want to have the curve that's the straight line from the start to the end. That's, I almost want to say 100%. Maybe there's like one example in a past paper somewhere where like they've given you a non-straight line, but almost all of them are just straight lines. So don't stress. Most of your curves, most of the curves that you actually have to deal with are just going to be straight lines. Or if they're not straight lines, it's going to be like a circle or something. It's going to be something super easy. Trust me. Okay, next, that's what a curve is. It's just a line in space that has a start point, has an end point, and we can parameterize it, which is really nice. Most of the time our parameter, also I didn't say this explicitly, but most of the time our parameter just varies between 0 and 1. So for example, a really easy parameterization is if you have a function that goes from a to b, you can parameterize it as a times 1 minus t times b times t. The reason for this is that if you sub t equals to 0, you get a. If you sub t equals to 1, you get b, and then as you vary t, the line just sort of smoothly moves from a to b, which is very lovely. Okay, that's what our curve is. Next kind of fundamental building block of a vector calculus is our idea of a vector field. So vector calculus, I didn't actually mention at the start, but it's basically looking at how we can describe things that are described by vectors, which is very important because there's a lot of, when we're doing stuff like physics, there is a lot of important properties that are described by vectors, which is really, really hot. And so we want to be able to describe what's going on with those vectors, which is really, really cool. Now, a vector field is basically something that maps a particular point into a three-dimensional vector field, where basically your space is filled up with a whole lot of vectors pointing in a whole lot of different directions with a whole lot of different magnitudes. Looks something along the lines of this, which is very cool. Most of the stuff that we're going to be dealing with here are dealing with vector fields or vector functions. It's very, very cool. Now, a line integral. This is essentially what we're going to be dealing with now is just a whole bunch of different ways of defining like funky variations of derivatives on vector fields and funky variations of integrals on vector fields. A line field is a curve that basically you have some line inside your vector field and you want to take the integral over it. The integral over the field over that particular curve here is defined by this funky function here. You can use any form of this equation, I would say. So the notation for the vector integral looks like this. Quick side note, I know with integrals, a lot of people really like visualizations of them. Because it's nice to see like, oh, what is the physical interpretation of this integral? But I'll be honest, most of these vector integrals don't have really nice or simple interpretations. So a lot of the time it's nicer just to, I mean, if you want to Google some, that's great. But I would honestly, I kind of understand them through the formulas. That's kind of the way that I would interpret them. Now, any of these formulas are nice. I would say these first two formula are the main ways that you're going to evaluate it. In fact, I would say most of it's going to come down to using this second formula. Once again, like a lot of stuff in this course and a lot of stuff in multivariable calculus, it's quite computationally heavy. Like it's just going to be you evaluate your function, you differentiate it, and then you sub in your different points, which is really cool. The reason I say that is because you may notice this third form is literally the second form, just like condensed. So if you dot product the derivative of a curve and multiply it by the function of the curve, you will end up with that top thing up there. One of our non-like geometric interpretations, but our physical interpretation of a line integral tells us how much the work the vector field f does as you move something over that particular curve there. So you can use it to evaluate things like work, and yeah, it's very, very fun. Let's have a cheeky quick practice at doing this. So a force field F is given by the function F equals 2y plus 2y times I, x, y, z times j, and 3e to the x plus y times k. And the path C is the straight line that goes from 431 to 635 in R cubed. We want to find a parametric representation for the path C and evaluate the work in the integral over f dr. Now, the first thing to notice is that our curve, just as promised, is just a straight line, which is really, really exciting. So our super, super easy parametrization for C of t is just going to be, we go from 431 times that by 1 minus t plus 635 times that by t, where t goes between 0 and 1. Very cool, very fun. We love that. I absolutely stan a nice straight line. Now from that, what we're going to do is basically just use this formula to substitute all of our values in. Now, these a and b in this formula here, I didn't really explain what it is, but it's basically the minimum value of t and the upper value of t. One of the reasons why this parametrization is really nice is because it means our lower value of t is 0, our upper value of t is 1, which means in this formula, almost always the bounds end up being 0 and 1, which generally are quite easy to evaluate. From there, what we want to do is we want to figure out what the derivative of y of like x, y, and z of t are. So to do that, what we're going to do is we're going to substitute in, I guess we could sort of condense this formula c of t. So we can say c of t is going to be equal to 4 times 1 minus t plus 6t, and then 3, 1 minus t plus 3t, and then 1 minus t plus 5t. We can combine most of our t's together, so that gives us 2t plus 4, and then just 3, and then what's that last one going to be? 4t plus 1. That is our expression for c of t. And then from there, we have expressions for x, y, and z. And so it's just going to be essentially a bit of a cheeky chug and plug. So our formula is we're integrating from 0 to 1 of f1 of ct. So f1 is our 2y. So we have 2 times y, and in this case, y is just 3. So it's going to be 2 times 3 times our derivative of x with respect to t. So our x is 2t plus 4. If you differentiate that, you just get 2, which means that's also just going to be multiplied by 2, which is very fun. So then we have f2 times c of t. F2 evaluated at the point c of t. F2 is x, y, z, so it's going to be all these three multiplied together. Which, looking at that, that's not going to be quite as fun as our first one. So our first one was really nice. I might just quickly condense that. It's 2 times 3 times 2, which is going to be 12. Plus, now we multiply them all together, which is exciting. However, never mind. What we can say is we're then going to multiply it by the derivative of y. Y in this case is just 3. So if we differentiate it, it's 0. So it's going to be x times y times 0. So we don't actually have to evaluate it, which is very nice. Because I was just fully about to have to do like 2t plus 4 times 3 times 4t plus 1, which like sounds exhausting. And so then finally, we just have to evaluate our final thing, which is going to be 3e to the x plus y if we sub in 3e to the 2t plus 4. And I know that on my thing I've got like the arc banner up there, so I don't want to get the arc banner botched up. So I'm going to scroll down a little bit, plus 3, and then we multiply it by the derivative of z, which is the derivative of 4t plus 1, so that's going to be times that bad boy by 4. And now we just integrate that with respect to t. So it's just going to be a matter of condensing all of that down. So now that's equal to the integral from 0 to 1 of 12 plus 12e to the 2t plus 7 dt. Integrating that, that gives us 12t plus 6e to the 2t plus 7 from 1 to 0. When we sub in 1, we get 12 plus 6e to the 9, minus when we sub in 0, that goes to 0. Be careful, this term doesn't go to 0, so it's plus 6e to the 7, which means when we evaluate that, that gives us 12 plus 6e to the 9 minus 6e to the 7, and that is our line integral, which is very exciting. And so I guess we could say, because we were trying to evaluate the work in the integral, it's going to be measured in joules. Hopefully that makes sense to everyone. Once again, it's just very computationally heavy, which is very exciting. Okay, so that's our solution, I'm pretty sure. Next thing that we're going to look at quickly is divergence and curl. Now, divergence and curl are essentially variations of the derivative to vector fields, they essentially measure two different things. So divergence measures how quickly a particular field spreads out. So I guess a classic one, particularly like in electronics and stuff, is how quickly like an electric field might dissipate across somewhere. Also might measure how quickly heat is spreading out from a particular heat source, or how much it might be spreading back in if it's sinking in instead. Could also be talking about like pressure flow if you've got like a water source and how like water is spreading out of there, something like that. Divergence, if it's positive, it means that you've got a source. If divergence is negative, it means you've got a sink. And it's pretty nice and easy. It's basically just the sum of all of the partial derivatives of your function. So it's sort of like if your gradient is all of your partial derivatives in vector form, your divergence is your partial derivatives summed up together. Now, one quick note, one thing that I want to draw to your attention is that the divergence of a function is a scalar value. It should just be a number, right? If you end up with a vector after taking the divergence of something, you're doing it wrong. Which is unfortunate. But yeah, the way we notate this is we do the divergence of something, like we write nabla.f is equal to, and then we just evaluate all of the functions. And finally, our other thing is curl. Curl has a fairly intuitive name because it basically measures if you have some particular point, that's the point you're taking the curl at. It measures how much your vector field circulates around that point. So it's sort of like if divergence measures the divergence, how much it spreads out, your curl measures the curl, so how much it turns around, rotates around a particular point. If your curl is 0, that means your field is irrotational. Basically, it's just spreading out exactly from your point. And there are lots of things in life that are irrotational, which is very, very fun. Now, the way that you take your curl, the way that I like to think about it is you're basically kind of like taking the cross product of all of your derivatives with your function. So all of your partial derivatives. It's essentially you take your essentially whichever rule that you memorized back in first year to take your cross product, you do the same thing with your derivatives and your function. So I know for me, I don't know what you would call this rule, but my rule that I like to think about is like physically drawing crosses. So like you cross those two, you cross these two, you cross those two, that then somehow manages to evaluate it, which is very fun. Some people like to do kind of the like little crosses here where you like cross those things. However you like to do it, you're just taking the cross of a divergence. So to be honest, if you don't understand curl, my first port of call would be go back and look back at your cross product from first year, because once you understand that, you probably understand curl as well. Now, one really, really important theorem about curl is that if the curl of a function is 0, that means that that function must be the gradient of some other function, which is really, really useful. Because it allows us to evaluate some integrals really, really quickly. So the TLDR of this is basically if you take the curl of something and the curl of that is 0, alarm bells should be ringing in your head that, oh, this function is probably the gradient of another function. And the reason that that is super, super nice is because it allows us to evaluate some line integrals basically as though they were like, you can use essentially your fundamental theorem of calculus to evaluate line integrals, where instead of having to do your whole freaking formula back up here, instead you can just basically sub in your 2 points. If your curve goes from A to B, all you have to do is sub in the function at those particular endpoints, and that will then give you your function, which is really, really cool. So let's have a cheeky quick practice. So consider the scalar field phi of x, y, z equals x times e to the z minus 1 plus cos of y. And we are told let f equal the gradient of some function. Now our first question is, what is the mental blank. What is the curl of f? Now, if you've just been paying attention, we can say that if a function is equal to the gradient of another function, the curl of it must be 0. So even without going through and computing it, we can say that the curl is equal to 0. I can't remember how many more questions I have. I have a little bit more to go, so I won't actually go through and evaluate it. But if you want to prove to yourself that the curl is equal to 0, you can feel free to go ahead and actually compute, chug and plug all of those values in, because you will end up getting 0. Now, hence or otherwise, we want to calculate the line integral of f dot dr along the straight line C from that point to the other point. If we want to do that, all we have to do now is, because we know that f is the gradient of another function, all we have to do is we plug in our first point, we plug in our finish point into our function and then subtract the end point from it. So basically, we're going to do phi of 5 pi 1, and we subtract phi of 1, 0, 1. So just really quickly doing that, we're going to end up with 5e to the 0 plus cos of pi minus e to the 0 plus cos of 0. E to the 0 minus cos of 0. Cos of 0 is 1. Cos of pi is minus 1. E to the 0 is 1. 5e to the 0 is 5. So it's 5 minus 1 minus 1 minus 1, which is 3. Sorry, no, that's not 3. That's 2. That's how you can tell that maybe I've been going for a little bit too long. Okay, that's our divergence and curl. Here's another question as well. Unfortunately, I probably just don't have time to go through this one. If you want to, the answers will be on the slides. I'll go through it slowly so you can look at the formulas. Wow, you evaluate the curl. It's kind of gross. And then you do later stuff, which is very cool. As a general rule, divergence and curl, I would say, if there's like one thing that you haven't looked at, please look at them, because they are really easy to compute. They're really easy to evaluate, and almost certainly there will be questions which is just like, oh, calculate the divergence of this function. Like, they're really easy mark grabbers and ways to like get some nice straightforward marks on your questions. Okay, the very last thing we're going to take a look at is double and triple integrals. So if you think of a normal integral as calculating the area under your curve, a double integral is basically where you've got some like multivariable function and you're finding the volume under a particular area. So it's sort of like, here's your function. I'm really bad at drawing multivariable functions, but then you look at some square in your xy plane and you basically calculate what is the volume underneath here. For the most part, it's really, really straightforward, because you just evaluate one thing with respect to x, one thing with respect to y, and then that's how you get it. So just quickly to go through this problem here, we're evaluating the integral of xy squared dA from the parabola, where we're going from y equals 6 minus x squared, the line y equals x, and the y-axis. Now, because this area that we're integrating over here is really gross and really complex, what I would recommend doing is just very quickly sketch out what it actually looks like. So, first of all, we've got the line y equals x, which is going to be this line here. We've got the y-axis, so that's another one of our bounds, which is this bound over here, and then the parabola 6 minus x squared, which basically is going to start at 6 and then look something like that, which means the area that we are actually evaluating over is this area over here. In order to like precisely do it, we're going to really quickly have to figure out what this point is, but that's pretty straightforward because it's the intersection of 6 minus x squared and the point y equals x, which now that I think about it, maybe isn't as simple as I had hoped. So it's going to be x equals 6 minus x squared, which is x squared plus x minus 6, which actually is not too bad because that's going to be x plus 3x minus 6 minus 2, I think. So our point is presumably going to be x equals 2, which gives us y equals 2. So this probably, I'm hoping, is going to be the point 2, 2, which is very exciting. Okay, so that gives us our bound. So we can sort of zoom in on this triangle, right? This little triangle that we're integrating over. So we have the y-axis, which goes from 0 up to 6. We've got this little integral section over here, which goes from, this is the graph y minus x squared, and then we've got the line y equals x, which goes up to this point 2, 2. Now, when we're integrating over it, we basically just need to think of some way of being able to completely cover this without bounds. Now, It doesn't actually matter if you're going to be integrating over x or y first. You would usually choose it based off of which one's going to be easier. I think in this case, it's probably going to be nicer to integrate over x first. Sorry, it's probably going to be nicer to integrate over y first, just because y is where we're hitting these two gross looking functions. So we can integrate, we can set the bounds of our y function as we're going from this point x. So essentially wherever our lower point of y is, it's wherever x is, up to this upper point of 6 minus x squared. The reason, just to sort of see why it's easier for x, is because if it's easier to integrate over y instead of x, is because if we were integrating over x, we would have to re-express all of these functions in terms of y, which is easy for this one. It's just going to be y, so it would be the integral from y. But then our top integral would be like the square root of something gross. Square root of 6 minus y, I think, which is like not fun to integrate over. So don't do that. And then once we've done that, our x just varies between 0 and 2, so we can integrate x from 0 and 2. So then we're doing x y squared dy dx, and we can evaluate that. So when you're evaluating that, you just sort of treat your x like constants, which is very fun. And when you evaluate your y, you should when you're integrating with respect to x, you should just treat your x as constants. And then when you're integrating with respect to x, hopefully, if you've done your integration right, there shouldn't be any y's left in the first place. Just to really quickly show you what I mean, if we're evaluating this integral, we're going to get the integral from 0 to 2 over xy cubed divided by 3, where we're subbing in 6 minus 2 squared, and x dx. So just really quickly evaluating that, that's 0 to 2 of x times 6 minus x squared cubed over 3 minus 3 times x all cubed over 3 dx, which you can then evaluate and you could probably expand and then solve as an integral in terms of x as well. So our region looks like that. That's what we're evaluating over. That's how we integrate it, and we end up with 256. Now, one very last thing is that sometimes when we're doing double integrals, we like to integrate over circles or ellipses and stuff like that, in which case we transform our variable, instead of being in x and y coordinates, into being in terms of r and theta coordinates. Just to sort of show you why this is really nice, it's because if we were to integrate something like a circle, which pops up fairly frequently, if we were to do that in Cartesian coordinates, we would be doing like the integral from like a minus x squared up over our top and lower bounds, whereas if we were to do that in r coordinates, we're essentially just integrating theta from like 0 to 2 pi, and we're integrating r from 0 to wherever r is at, which is really super nice. And the only thing that you need to remember is your your parametric substitutions. So you substitute, instead of f, x, and y, you sub in r cos theta and r sine theta. And because of funky things with like polar coordinate transformations, you multiply by r as well. You multiply the whole function by r. If you're interested, it comes from, I think, the derivative or the determinant of the derivative of that matrix. Now that allows us to solve some fairly funky integrals, such as the integral of e to the minus x squared plus y squared, which is very fun, and I've got my whole working out here. But I know that I have gone well over time, and it is time for me to pass on to the wonderful, the incredible Master William. So thank you all very, very much for bearing with me amongst all of this wonderful times. I will just check that Mr. William is ready to come on. But yeah, thank you all very much for coming along. If you have any other questions, chuck them in the chat and I'll take a cheeky look. Otherwise, I will hand you over to the very, very capable hands of Mr. William Wu, who will be taking over the stream from now. So, Mr. William, hands over to you.
Okay, hello. Now we'll be moving on to the matrices, which is relatively tame and well mature compared to the first part where Tin had to go through. Thank you, Tim, for that. You don't have to worry about your work or, any other life commitments. All right, it's mostly just revision. So let's get into it. So I have an example. I have a matrix A, and it's given to us that is diagonalizable with eigenvalue of -2 and 1. I want to verify that the vector 2, 1, 1 is an eigenvector of A, and I want to diagonalize the matrix A. For simplicity's sake, I'll just be labeling the vector v1 as 2, 1, 1, and we'll refer to that as our eigenvector from now on. So to verify eigenvector v1 is an eigenvector of A, we kind of just want to plug it into the equation, like multiply it by A, and if we return to us like a scalar multiple of v1, then we know for sure that it is an eigenvector of A. So we'll do just that. So multiplying the eigenvector, multiplying v1 with the matrix A, it gives us -2 v1. So this means that v1 has a eigenvalue of -2. So lambda 1 equals to -2. And now next we want to try to diagonalize the matrix. A matrix is diagonalizable if okay, I haven't gone to the definition yet. Okay, well, before we diagonalize the matrix, we will need, I'll just go to the definition here. So a matrix is diagonalizable if we can write it as in the form of A equals to Q dQ inverse, where Q is a matrix made up of its eigenvectors, so v1, v2, v3 here, because A is a 3 by 3 matrix, and D is a diagonal matrix with eigenvalue of lambda 1, lambda 2, lambda 3, that corresponds to each of the eigenvalues. So before we diagonalize it, we'll need to find each of the eigenvalues and the eigenvectors. So basically from first year, to find eigenvalue and eigenvectors, we've been doing it through using characteristic equations. So let's say we have a 2 by 2 matrix equals to A, B, C, D. To find the eigenvalue and eigenvectors, we will need to find the determinant of A, which is equal to, find the determinant of A minus lambda I, which is A minus lambda, B, C, and D minus lambda, like this, which will give us A minus lambda, D minus lambda minus C times D. And basically want to solve for 2 lambdas here, and that would give us our corresponding eigenvectors. Now this is a 3 by 3 matrix, so doing that may be a little bit tedious, but instead we will want to use the information that we are given to us. That is, we have eigenvector 2, 1, 1, and we know that it has an eigenvalue of -2 and 1. So all we need to do is to find the last eigenvalue. Now to do that, we can use something called the trace of the matrix. So basically, given, let's say we use a 2 by 2 matrix again. So we have a matrix A equal to AB, CD. The trace of the matrix, which is just adding the diagonals, is equal to the sum of eigenvalues. So trace of A is equal to A plus B, which also happens to equal to lambda 1 plus lambda 2, well, lambda 1 and lambda 2 are eigenvalues of A. So to do that, we see that our matrix A here has the diagonal of this, and to put that all together, we have minus 2 plus 4 plus 1, which equals to 0. And we also have our eigenvalues here, so negative 2 plus 1 plus lambda 3. We want that equal to 0 because they should equal. And it's pretty obvious that lambda 3 is also equal to 1. Right, so we have our eigenvalues. So lambda 1 equals to negative 2, lambda 2 equals to 1, and lambda 3 equals to 1. And now we'll go on and find the eigenvalues of 1, because we already know, find the eigenvector of negative 2, because we already know the eigenvectors. Sorry, we can now go on to find the eigenvectors with eigenvalue 1, because we already know what the eigenvector with eigenvalue negative 2 is. So to do this, you want to do a v equals to v, because our eigenvalue is 1, and shifting the v to the outside, we have v minus v equals to 0, and we can pretty much just pull this out. Minus I equals 0, where I is the identity matrix. So, in R3, so it would just look something like this. And this will give us the kernel for A minus I, and what we need to do next is find the vectors that will span the kernel, so that and then that will give us the two eigenvectors corresponding to the eigenvalue of 1. So without going too much into the computation, we have that the vectors, the matrix minus 1, minus 1, minus 1 will give us negative 6 is 0, negative 3 is 0, negative 3, oh sorry, that's positive 3 is 0, which is exactly what we have here. And by doing some row reduction, we can see that this row and this row cancel out, and okay, that is very bad math. So this row will cancel out this row first, so which is okay, R1, R2, R3. So R2 minus R3 will make this row 0. So, and then we'll have R1 2 R3 minus R1. We'll get rid of this row. So we're left with only R1, and we can just divide that by 6, which give us negative 1, 0, and the rest of the matrix 0. And now we want to find the kernel that span this span this matrix. So what finding the kernel means is basically whatever vector we want to find a representation of the vectors, the set of vector v, such that this equal to 0. And we can do this simply just by solving negative 1, 0, 0, 0, 0, 0, 0, like so. I'll get a second page for this. Okay, so we have our negative 1, 1, 0, 0, 0, 0, 0, 0, 0. I want to solve this for this. All right, so and we can see that it has two non-leading columns, which means we must have two parametrizing factors. So we can just let x2, 3, oh, it makes more sense. I'll let x1 equals, so our non-leading columns are the x2 column and the x3 column, because they don't have a leading coefficients like the x1 column has. So we'll let x2 equals to u2, and then we'll let x3 equals to u3. And since all these are 0, we don't really have to do much work on them. We'll just have 1 negative x1 equals plus x2 equal to 0, but x2 equals to u2, so x1 equals to x2, and x1 also would then equal to u2. And put this all together, we'll have something like this, x1, x2, x3, which is u2, u2, u3. Or we can actually pull this apart. Kind of like, because u2 and u3 are all scalars, we can write it as something like this. Oh, I got a doorbell. 1 second. Sorry, continuing on. We'll pull the u2 out first, and we get 1, 1, 0 plus u3 0, 0, 1. And so this is our, and so we get a linear combination of u2 1, 1, 0 plus u3 0, 0, 1, 1, and these two are linearly independent, and we can see, and they are of so they have a so then that will mean they will both those two, like the span of those two will just be spanning the kernel of our matrix here. And so which means that our v3 our v2 would be 1, 1, 0, and our v3 will be 0, 0, 1, and they both have an eigenvalue of 1. So lambda 2 equals to 1, and lambda 3 equals to 1. And we can just actually test this out here. So if you have a matrix, negative 1, 1, 0, 0, 0, 0, 0, and you want to solve for 0, like it makes intuitively sense if we let the first two x1, x2 be 0, and then so the last column x3 could, last row x3 could be whatever we want, because I have 0 times 0, 0 times negative 1, 0 times 1, and then we have whatever we want times by 0, which will always give us 0, so we get the 0 matrix. And the same thing with here. As long as x1 equals to x2 and the last thing is 0, we can have whatever we want, like times, like we can have 8 times 1 plus 8 times negative 1, and no matter what, as long as they're equal, we'll get 0, and then obviously the linear combination of these two will also give us solution to 0. So yep, that is our eigenvector, both of our eigenvectors for eigenvalue of 1. Now to diagonalize the matrix I've gone through earlier, a matrix A is diagonalizable if there exists a matrix Q such that A equals to Q dq negative 1, where D is an n by n eigenvalue entries to the diagonal, and Q is a matrix with the eigenvectors are arranged in order corresponding to the eigenvalue in D. To find Q, we just put all our eigenvectors together, which is v1, v2, v3, and obviously this means our D will be negative 2, 0, 0, 0, 1, 0, 0, 0, 1. And so we can, A is QD, Q inverse. All right, so that is matrices, eigenvalues and eigenvectors. Now next we have conics and quadrics, and we just have an example of a conic slash quadric here. And you probably might know what this looks like. I think this is an ellipsoid, just because all the signs are positive, but I could be wrong on that. So in general, it's not too hard to classify shapes with only x squared and y squared and z squared terms like this one. And there are a list of rules we can use to identify the type of conics or quadrics. Conics are 2D and quadrics are 3D surfaces. But if we have multiple like extra terms, like axis terms like xy, yz, and xz, it can get a bit more complicated and messy. So we'll try and figure out a way to identify this, and yeah, we want to use eigenvectors. So for example, we have the quadric surface, 5x squared plus 3y squared plus 4z squared plus 4xz plus 4yz. I want to find the principal axis, the type of surface, and the points, if any, close to the origin. So for questions like these, we can always write our quadrics in the form of x transpose ax, where x is just a vector in the form of x, y, z. So we want to find a matrix A such that when we do this multiplication here, we'll get back what we have here. So we want to find A such that x, y, z, x transpose A transpose equal to 1. And it might not be intuitive first because we have all these x's turned over here. You might be thinking like, how are we gonna find a matrix, right? We're gonna have to do it through trial and error. But like that, the way I think about it is we kind of just let A be like a matrix completely filled by 1. And that's 3 by 3 in this case because we are in R3. So then we have want to find, and then we times this by x transpose A and x transpose, right? Which will give us x squared, y squared, and z squared, xy, x, y, xz, yz, xz, and yz. If you multiply this out yourself, you find that they're symmetrical. And then we kind of just want to find the coefficients in front of all these terms, right? And we see that for x squared, y squared, and z squared, there are only like one term of each in the equation. So obviously we have that in front of these ones, we have 5, 3, and 4. Now moving on to the xy terms, we see that there are no xy terms in the equation, so these will just be 0. And then onto the xz terms, we have xz equals 4, but when we have like here, we have 2xz, right? So we want to split the 4 evenly between those two terms. So we'll have 2 and 2, and then the same with yz, it has a coefficient of 4. So and then we split the coefficient among the two yz that's over here. So 2 equals to 1, and this is our matrix A. Oh, there shouldn't be a 1 there. So this is our matrix A. Yep, so we find the eigenvalue, and then we want to find the eigenvalues and the eigenvectors of A. And then we'll diagonalize A into the form of QDQ, where Q is orthogonal, and then our new axis will be in the form of big X, which is called this big X. This big X will help us find the point closest to the origin and help us better identify what this shape is. So we're writing this in the form of x transpose AX equals to 1. We've done that. We found our matrix is 5, 0, 0, 3, 4, 2, 2, 2, 2, 2, 2. And then now we want to find the eigenvalues and the eigenvectors of our matrix. I just hit my elbow. So I guess there really isn't a good way of doing this other than just brute forcing it. So basically what we want to do is, like we've done before, want to find the such that determinant of this equal to 0. So we have 5, 0, 0, 1, minus 0, lambda, 3 lambda, minus 3 minus lambda. Okay, 3 minus lambda, 0. Oh my god, it's a 5 there. Bit too cooked. 5 minus lambda, 0, 3, 2, 0, 2, 2, 2, 2, 4 minus lambda. And we just want to solve this to find lambda. That is a little bit computationally intensive, and on the sake of time, we'll skip the calculation here, but you can check, we'll just take it for granted that it has a eigenvalue of 1 with the eigenvector with we have v1 equals to -1, -2, 2, 2, 2, and then lambda 1 equals to 1, v2 equals to -2 to 1, and lambda 1, 2 equals to 4, and we have v3 equals to 2, 1, 2, and lambda 3 equals to 7. And so given this information, we again want to do now this time I want to do orthogonal diagonalization, which is pretty similar to what we did before, but except our matrix Q this time is an orthogonal matrix, which means that Q should have determinant of 1, and all the columns v1, v2, v3 should be orthogonal of each other, which means that v1 transpose times v2 should give us 0, and each of them multiplying each other should also give them 0. So we don't know what this matrix Q is, but we can get some kind of hint, like with our eigenvalues and eigenvectors, and figure that out. So we just diagonalize it normally, like how we did before. So we have A equals to QD Q transpose, and we have that our Q is just the matrix of our eigenvectors, and D is our eigenvalues correspond to the eigenvectors on the diagonals. But Q is not orthogonal because the determinant of Q is obviously not 1. So what we want to do is we want to make the determinant 1. Nicely enough, though, we find that the eigenvectors are orthogonal to each other. So if we take this, v1 transpose times v2 is 2 minus 2. Wait, sorry, minus 4, and then plus 2, which is 0. And similarly, v2 transpose v3 transpose is -4 plus 2 plus 2, which will also give us 0. And you can check the rest yourself. But in general, when we have a symmetric matrix, symmetrical matrix A, its eigenvectors will always be if it's diagonalizable, the eigenvectors will always be orthogonal of each other. And for conics and quadrics, that's what we'll always be working with. We'll always be working with symmetric matrix A. So it makes it, when we find the eigenvalues and eigenvectors, it makes it nicer for us to find the orthogonal matrices. So now we want to turn this into a matrix with determinant 1, and we find, so basically we want that all these columns to have the length of 1. And it just happens so that they all have the same length. So if we want to find the length of v1, we get 1 squared plus 2 squared plus 2 squared, which is √9. So v1 has the length of 3, and so does the rest of them. So what we need to do is our new matrix Q, let's call it Q dash, is 1/3, -4, -2, 2, -2, 2, 1, 2, 1, 2, like that. Okay. So that's what we have here. And now with the same rule, we have A equals to Q transpose D Q transpose inverse inverse. Now with orthogonal matrix, its transpose equals to its inverse. So that saves us trouble of trying to find the inverse of a 3 by 3 matrix, which can be a little bit annoying. So that's what we have here. And now we just want to remember that since we have x transpose a x equals to 1, we also have that x transpose q d q transpose x also equals to 1. And we can rewrite this as this. So when we take a transpose of something, we basically flip them around and transpose it individually. So we can write it as that. And then notice that this looks very similar to what we had earlier, x transpose a x, right? But we can write this part as big X equals to Q transpose small x. This is big X. Okay. So we can have something like this. Q D equals to 1, which means we can also write our conics in the form of this. We can kind of think of this as like a change of basis. It preserves all the metrics of the original form, but we're kind of just changing the basis. It's like a linear transformation. Should be linear. Yeah, and now all I have to do is replace Q transpose X with the substitution of big X, big Y, and big Z. And this allows us to exploit our diagonal matrix. Since we have our diagonal matrix is just of 1 0 0 0 0 4 0 0 7, all right, and then doing this, we'll get big X squared plus 4y big Y squared plus big 7 big Z squared equal to 1. So this will be our new basis and new form for our original quadrics, and I think this is an ellipsoid just because all the signs are positive. So, yep, and that's what an ellipsoid looks like. You should have your lectures note should have like a definitive version of how to identify the basics quadrics and conics, so you'll be fine. And now all we have left to do is to find the principal axis and the point closest to its origin. Now, before we go on, we have that. We found the shape in our x domain. So our big X is the big Y, big X, big Y, and big Z domain. And we can kind of change them between the big X domain and the big Y and the small x domain through our orthogonal matrix Q. So to go from our small x to our big X, we will just apply a Q transpose to small x, and we get it into our big X domain because that's how we have defined over here. And to go from a big X to our QX domain, we have that small x equals to Q big X, like that. So if we found the closest point to the origin on our big X domain, then we can just apply our matrix Q to it, and we will have our we'll have it in our small x domain. Now note that Q is orthogonal, so it is invertible, and naturally we can think of matrix as transformations and mappings. Invertible matrix means that it will have a linear transformation. So not okay, I don't want to say that because I don't want to misinform people. Yeah, Q will have a bijection, which is a 1-to-1. So we have a 1-to-1 mapping from the points of on the big X domain to the small x domain. Right, so to find the closest point to the origin in our big X domain, remember that our big X domain is x squared plus, we have the equation of x squared plus 4 squared big Y squared plus 7 big 7 squared equals to 1. And to find the closest point to origin, we'll obviously want this to be 0. Y squared plus 7 7 z squared plus 7z squared minus 1 equal to 0. And we want these solve to 0. So some obvious choice will be make is just by setting each of the big X, big Y, big Z equal to 0, and just have and just kind of setting the X and Y and Z to their respective coefficients, 1 over the square root of the respective coefficients. So we can try that out. So we have, by letting X and Y, by letting Y and Z equal to 0, we have the point Y0 is 1, 0, 0. By letting X and Z equal to 0, we have 0, negative 1 to root squared 0. And by letting X and Y equal to 0, we get 0, 0, 1 over root 7. And we see that this has the smallest distance to the origin, which is just 1 over root 7. And this has the distance to origin of 1 over root 2, also 1 over 2, and this has the origin of 1 over of 1. So this, our point V, our vector V here, our point V here, is our closest point to the origin in the big X domain, but we want to put that into the small x domain. So we'll do what we said earlier. We'll do what we said earlier of do a change of bases. So going from big X to small x domain, we'll have big X times Q equals to small x. So we'll have 1 over root 3, I think I forgot what the matrix was. Let me just check. One. Okay. Yeah, no, I forgot that again. Okay, I'll just write. I'll basically it is just our eigenvalue vectors on each of the respective columns. So times it by the point 0, 0, 1 over root 7 should give us our coordinates in our small x domain. Now next, we also want to find the principal axis of the ellipsoid. And it just happens so the principal axis of the ellipsoids are our eigenvalues, our eigenvectors, but orthogonalized, not normalized. So they all have length of 1. So that will be the principal axis, and the point closest to origin is this. And multiplying this with our orthogonal matrix, we will get points 3. We'll get these points in our small x domain. All right, that is conics and quadrics. Next up, we have basic matrix systems and differential equations. This is a basic ODE. One way of solving this is just to notice that this side, the right hand side, looks awful like a matrix, and the left hand side looks awful like a vector. So you can write it out as kind of like a vector basis. The first derivative of y is equal to a times y, while matrix A is -3, 4, 8, and 1. And we kind of want to solve this to such that these two will give us the same thing. Okay, and to solve this kind of system equations, we have this nice theorem that says the general solution to any of these kind of theorems is in the form of, and y is in the form of a constant coefficients multiplied by the eigenvectors times by e to the power of the eigenvalues times by t. And the eigenvalues and eigenvectors are corresponding to our matrix A, which I found is -3, 4, 8, 1. Since we have enough time, and this is a 2x2 matrix, it shouldn't take too long for us to go through this. I'll just go through this just to refresh those of you that, for those of you that have forgotten how to find eigenvalues and eigenvectors. So, want to find a determinant of A minus lambda I equal to 0. That means we will want to find -3 minus lambda, 4, 8, 1 minus lambda equal to 0. And we have our characteristic equation here just by multiplying that out. So we have -3 times minus lambda times 1 minus lambda minus 32. And times multiplying out, we have -3 plus 3 lambda minus lambda plus lambda minus 32 equals 0. There should be a lambda squared somewhere. Oh, here. So we have lambda squared plus 2 lambda minus 35 equals 0. And we see that it simplifies down to lambda minus 7 plus 7 and lambda minus 5. And so we have our lambda 1 equals to -7 and lambda 2 equals to -5, equals to 5. And to find the eigenvalues, the eigenvectors, we'll want to find the kernel of A minus 7i, sorry, plus 7i because 7 is negative. So we want to have -3 plus 7, 4, 8, 1 plus 7 equals to 4, 4, 8, 8. And we see that these two roles are the same, so we can just reduce it into 1, 1, 0, 0. And again, to find the kernel of this we just want to solve this by 0. And we have, since I have one non-leading columns, we'll let x2 be t, where t is a scalar. And so x1 equals to minus x2 from the first row. And so x1 equals to minus t. And so we have that our vector v are, or all the vector in the kernel are of the form x1, x2, which is t minus t. So our eigenvector 1 will correspond to the eigenvalue of -7, will just be 1 and -1. And similarly, we can do that for the same thing to find the eigenvectors for eigenvalue 5. So I want to find the kernel of A minus 5i. I won't go through that here because that just should be pretty straightforward now after we've done this example with 7. So I'll just leave you to try this out at home. And then we find that the respectively phi also has an eigenvector of 1, 1, 2. And now all we have to do is put this back together to find our general solution. So using the theorem we have here, we can just chuck everything together, which will give us C1 out, which is an arbitrary constant, and C2, which is another arbitrary constant. And so this is our V1, and this is our V2, and this is our lambda 1, and this is our lambda 2, right? So that concludes this session. I just realized I forgot to check chat the whole time. Let me just quickly check if there was any questions. No, okay, all good. All right, thank you guys for tuning in today. I hope you guys have a good rest of the